The aircraft ignition system and its many components are often taken for granted because they are so reliable. But even though we seldom think of it, much of the dependability and high performance of our modern aircraft engines depend on these vital components. Because it is the responsibility of the aviation technician to maintain these systems in their best operating condition. The following two-part training program has been prepared on this important aircraft system. It is hoped through this presentation, maintenance of aircraft ignition systems and safety in the air will be improved. In Part 1, we will see how high voltage is generated in an aircraft magneto and how it is distributed to each cylinder at the proper time. We will also review the spark plug, as well as the ignition harness, which carries high voltage from the magneto to the spark plugs. In Part 2, we will look at practical aspects of magneto timing, internal timing, timing the magneto to the engine, the proper way to service aircraft spark plugs, and check aircraft ignition harnesses. To begin with, an automobile ignition system uses the battery to provide electrical energy to start the car. An airplane, however, employs a different method to start the engine. This starting system is completely independent of all other systems. Here, the ignition system draws energy from a self-contained high-voltage magneto. In both types of ignition systems, the starting current flows through the primary winding of a coil as it goes from its source to ground. When current flows in this winding, a magnetic field is created. The intensity of this magnetic field directly depends on the amount of current flowing. Now, if another winding, called a secondary winding, which has many times more turns than the primary, is wound on top of it, any change in the primary current will immediately induce a voltage into the secondary. The amount of voltage generated is determined by two things: the ratio of the number of turns in the two windings and the rate at which the current changes in the primary. An easy way to increase the rate of current change in a magneto is to install a set of breaker points in the primary circuit. These points are timed to open the circuit and stop the flow of current at the exact moment a spark is needed to ignite the fuel-air mixture in the cylinder. When these breaker points open and the flow of primary current stops, the magnetic field linking the primary and the secondary winding of the coil collapses. This immediately induces a high voltage into the secondary winding. This high voltage finds a path to ground by jumping the gap in the spark plug. The current flowing through the breaker points when the cam starts to separate them will continue to flow. This creates an arc and will burn the contacts. To prevent this arcing, a capacitor is placed across the contacts. Now, as the points begin to open, their resistance will increase, causing current to flow into the capacitor rather than producing an arc. The generator portion of a magneto consists of a permanent magnet supported in ball bearings, which rotates inside a laminated soft iron frame. When the poles of this magnet are aligned with the pole shoes, the magnet is said to be in its full register position. This means there is a maximum number of magnetic flux lines in the frame. Now, as this magnet rotates 90 degrees from full register, it is said to be in its neutral position, preventing the flux from flowing in the frame. The primary winding of a coil is actually wound around the magneto frame. So, as the magnet inside rotates, the flux will change inducing a voltage into this winding. This causes the primary current to flow. When current flows in the primary winding, it also produces a magnetic flux, which, according to Lenz's law, opposes the change that causes it, and the final or resultant flux causes the primary current to reach its maximum. This does not occur at the neutral position of the magnet, but instead a few degrees beyond neutral of magnet rotation. To obtain the greatest rate of flux change, the breaker points must be timed to open at the exact instant the primary current reaches its maximum. The number of degrees the magnet rotates beyond its neutral position is known as the E-gap angle. It is at this E-gap position that the breaker points must be timed to open. This angle varies with the magneto design, but is specified by the manufacturer in his service information. Now, when current flows in the primary winding, the magnetic field caused by this current expands outward until it completely encircles the many turns of the secondary winding. And when the breaker points open, this field immediately collapses, cutting across the secondary winding. As a result, an extremely high voltage is induced. The amount of this high voltage is determined by two things: the rate at which the lines of flux are cut, and the ratio between the number of turns in the primary and secondary windings. In a typical magneto, the secondary voltage is approximately 100 times that of the primary. Now that we have discussed the theory of magneto operation, let's try a couple of questions. At what position do the breaker points open? Is it when the rotating magnet is in its neutral position, before it reaches its neutral position, or after it passes its neutral position? If you have answered, after it passes its neutral position, you were correct. The E-gap angle is that position where the primary current is the greatest, and the breaker points are timed to open a few degrees after the magnet passes neutral position. Here's another question. Which two of these four factors determine the amount of voltage induced into the secondary winding when the magnetic field collapses in the primary? Is it A, the turns ratio between the primary and the secondary; B, the number of turns in the primary winding; C, the amount of flux change; or D, the rate of flux change? The correct answers are A and D. The amount of voltage induced by the collapse of a magnetic field is determined by the turns ratio of the two windings and the rate of flux change. Over the years, the magneto has evolved from an open magnet wound rotor device employed on early aircraft engines into the simple, compact, and highly reliable units found on our modern aircraft. These magnetos are contained in a cast aluminum housing, which features a laminated soft steel frame used to conduct flux lines from the rotating magnet. This two-pole permanent magnet is driven from an engine accessory drive and rotates within the housing. The close fit between this magnet and the pole shoes minimizes the loss which occurs when flux lines cross an air gap. The coil assembly of the unit contains both primary and secondary windings tightly wound around a laminated soft steel core. This core is held in the magneto frame by special clamps, creating a tight fit minimizing the opposition to flux flow. In the coil itself, one end of the primary winding is grounded, while the other end attaches to the breaker points. On the secondary winding, one end is internally connected to the primary. This allows the high voltage to leave the coil at the spring terminal. A cam is securely fastened to the shaft of the rotating magnet. As it turns, it presses against the cam follower to open the breaker points. The fixed contact is grounded, while the contact on the spring is insulated from the ground by being connected to the primary winding. The capacitor is housed in a steel case, which serves as a ground connection, and the single lead coming from the center connects to the insulated breaker point. A special gear keyed to the magnet shaft drives the distributor electrode. This directs high voltage to the spark plugs in proper sequence. The teeth on the two gears are marked to show how they have to mesh. This aligns the distributor electrode to the contact in the distributor housing to the same time the breaker points open. A spring-loaded carbon brush is located in the center of the distributor gear to pick up high voltage from the spring contact of the secondary coil winding. By doing this, high voltage is then directed through the electrode to one of the brass contacts in the distributor block. At this point, the high voltage jumps the gap between the electrode and its contacts and is routed to the spark plug. Ignition leads attach directly to the distributor block and provide the path for high voltage to reach the spark plug. One of the problems with a magneto during starting is that at very low speeds, the magneto does not generate enough voltage to produce a good hot spark. So some provision must be made for starting. To overcome this problem, an impulse coupling is used. To understand how an impulse coupling works, remember that the magneto drive shaft does not connect directly to the engine, but rather to a cam plate coupled through a heavy spring to the main body. When the engine is turned with the starter, one of the flyweights will engage a stop pin. This holds the magnet in place as the engine continues to turn. As the engine rotates, the cylinder piston to be fired nears the top center position. The body of the impulse coupling contacts a ramp of the flyweight to slip it off of the stop pin. This causes a spring to spin the magnet, producing a hot spark, one that is late enough so the piston is not pushed back down before it passes over top center. As soon as the engine starts, a centrifugal force holds the flyweights inside of the body, away from the stop pins. The impulse coupling now serves as a rigid connection between the magneto and the engine. Since an impulse coupling is not adequate for starting all engines, a vibrator-type starting system is often used. This type of system, produced by the Bendix Corporation, is known as the shower of sparks system, primarily because it produces a high-intensity series of sparks rather than a single discharge each time a cylinder is ready to fire. The left magneto used in this system has an extra set of breaker points known as retard points. These are operated by the same cam as the other points, but they break or open later. They open when the piston is at top center to prevent the engine kicking backward. In addition to this extra set of breaker points, this type of system uses a vibrator to produce pulsating direct current, which is boosted in voltage by the magneto coils. Finally, a special ignition switch is also required by this system. When this ignition switch is placed in the start position, three important things happen. First, the right magneto is grounded, so its early spark will not cause the engine to kick backward. Then, the vibrator is energized, sending pulsating direct current into the left magneto, where it flows to ground through both the normal and the retard breaker points. This energizes the starter, and the engine begins to turn over. It is important to remember the normal breaker points open when the piston is about 30 degrees before top center of the compression stroke, and the retard points remain closed until the piston reaches top center. And as long as either set of points is closed, the pulsating current passes to ground without accomplishing anything. But as soon as both sets of points open, the pulsating current passes to ground through the primary winding of the magneto coil. And in doing so, it induces a high voltage into the secondary, sending a series of sparks to the spark plug as long as both sets of points are open. As soon as the engine starts and the pilot releases the switch, it automatically returns to the both position. This is with the right magneto ungrounded, the starter and vibrator off, and the retard points out of the circuit. Now, before we leave the magneto, let's check our understanding with a couple of questions. How is high voltage conducted from the coil to the distributor rotor? Is it A, by a solid connection, or B, through a spring-loaded carbon brush? The correct answer is B, a spring-loaded carbon brush in the distributor gear, which presses against the spring contact on the coil to conduct the high voltage from the coil to the distributor. All modern aircraft use magnetos to supply energy for ignition, but they do have limitations. What is the main limitation of a magneto ignition system? Is it A, dependent on the aircraft electrical system, or B, needs an auxiliary system for starting? Answer B is correct. The intensity of the spark from a magneto depends on the rotational speed of the magnet. And when the engine is turned slowly, as it does during starting, the magneto does not produce a hot enough spark. This requires the use of impulse couplings or vibrators. Generating high voltage is only 1/3 of ignition system operation. We must get this high voltage to the spark plug with a minimum of losses, and it must be able to jump to ground inside of the engine cylinder to produce a spark hot enough to ignite the fuel-air mixture. Anytime a spark jumps a gap, there is electrical energy radiated out, not only from the spark plug, but also from all of the wires in the ignition system. This energy can be received on the radio in the airplane, causing poor reception of communications, as well as wrong indications on navigational equipment. To prevent this unwanted noise, the entire ignition system must be shielded. The magneto, the spark plugs, and all of the wiring is usually encased in a metal covering or shielding. This intercepts radiated energy and directs it to ground, where it cannot cause any interference. The wiring used to conduct the high voltage from the distributor to the spark plug may be composed of several strands of stainless steel wire, or a coiled conductor made up of one piece of wire, wound into a tight spiral and encapsulated by insulation. An insulator, having a high dielectric strength, surrounds the center of this conductor. And around this insulation is a metallic braid that's protected by a tough, abrasion-resistant covering. The end of the conductor usually has a spring that presses against the inside of the central electrode of the spark plug. And a silicone rubber cigarette about an inch long insulates the high voltage from the steel shell. The end of the shielding is then attached to the terminal elbow. When the lead is inserted onto the spark plug and the terminal nut tightened, there is a continuous metal shield around the spark plug and lead, all the way to the magneto. At the magneto end of the harness, the lead's attached to soft rubber grommets, which fit into the distributor block and form a watertight seal. And the magneto end of the shielding is terminated in the metal plate which holds the grommets in place. It is extremely important when the lead is put onto the spark plug that there is no strain on the terminal insulator. Because of the varying locations of the spark plugs in the cylinders, ignition leads come in several types of terminal ends. Some have a fixed angle. Some are straight, while others may be straight but can be formed to the proper angle and held in this position by a special clamp. At this point, let's try a question about leads before we go into our next subject. Why are aircraft ignition leads encased in a metallic braid? A, to provide mechanical strength. B, intensify the spark. Or C, minimize radio interference. The correct answer is C. It minimizes radio interference by passing radiated electrical energy to ground. Now that we have seen how electrical energy is generated and delivered to the spark plugs, let's analyze the spark plug itself. The heart of an aircraft spark plug is a glass-hard ceramic insulator. This prevents the high voltage from passing to the engine at any place other than across the electrode gap. The copper cord nickel alloy center electrode is held in this insulator to provide a terminal for high voltage. The entire spark plug is encased in a steel shell, crimped into a single unit, with copper gaskets sealing the insulator in the shell. This prevents any leakage of the hot, high-pressure gases during combustion. An extra heavy ring of nickel alloy is bonded into the firing end of the shell to provide a place for the spark to jump. Some spark plugs have 2, 3, or even 4 ground electrodes, depending on the manufacturer involved. If the aircraft has no radio equipment, it may use an unshielded ignition system. In this case, the spark plug only needs a brass knob on top of the ceramic insulator for ignition lead attachment. But the vast majority of modern aircraft do have radios, and shielded spark plugs are required. There is one problem that comes from a shielded ignition system. This is called the capacitive effect of the shielding. Anytime we have 2 conductors separated by an insulator, as we have in a shielded ignition system, we have basically a capacitor which stores electrical energy each time a spark occurs. Now, this means when the spark jumps the spark plug gap, the conductivity across the gap tends to increase. And as the spark begins to die out, the energy stored in the shielding will feed back into the conductor, prolonging the spark. This prolonged spark will cause fast erosion of the spark plug electrodes. To minimize this condition, a resistor is usually built into the insulator between the terminal contact and the center electrode. This resistor decreases the duration of the spark and does not affect its intensity. Tetraethyl lead is used in aviation gasoline to help stop the problem of detonation. But this lead oxide tends to accumulate in the firing end cavity of the spark plug. These hard, gray, clinker-like deposits form when lead-rich combustion products condense and build up inside the firing cavity. As a result, high voltage will leak across these deposits, rather than build up to jump the spark plug gap. To minimize this lead buildup, especially in severe lead fouling conditions, fine wire spark plugs have been developed. These spark plugs use two extremely small platinum or iridium ground electrodes to provide a place for the spark to jump from the center electrode. This opens up the firing end to allow combustion products to be easily scavenged before they can condense and form lead deposits. The small mass of fine wire electrodes and the heat-resistant material from which they are made also make it possible to operate these plugs at higher temperatures, preventing the formation of heavy lead deposits. This increases the effectiveness of fine wire spark plugs in severe lead fouling applications. Now, before we look at other characteristics of spark plugs, let's review a couple of questions to check our understanding. Question: why is a resistor used in aircraft spark plugs? Is it to cut out radio interference, minimize electrode erosion, or decrease the intensity of the spark? The correct answer is minimize electrode erosion. It is the shielding which cuts out radio interference, while the resistor decreases spark duration. Next, what are the main reasons for using fine wire spark plugs? Is it to minimize lead fouling, get a hotter spark, or to allow the spark to jump at a lower voltage? Both to minimize lead fouling and to allow the spark to jump at a lower voltage are correct. The more open firing end and the higher operating temperatures allow fine wire spark plugs to minimize lead fouling problems, and the small area of fine wire electrodes allows the spark to jump at a lower voltage. At this point, let's look at other spark plug features that distinguish one plug from another. First, there is the shell thread size. These are metric dimensions, and almost all current production engines use 18mm spark plugs. Some Franklin engines, however, require a spark plug with a 14mm shell thread. The reach of a spark plug is thread length of the shell. The required reach is determined by the cylinder head design. A long reach, or 18mm spark plug, has 13/16 of an inch of threads, while a short reach spark plug of the same size has only 1/2 inch of threads. The heat range of a spark plug is measured by the ability of the nose core insulator to conduct heat into the spark plug shell and then into the cylinder head. A hot spark plug has a long heat flow path and it is used in an engine where cylinder temperatures are low and require a longer nose insulator. This will allow it to reach temperatures high enough to burn off contaminants and prevent plug fouling. A cold spark plug, on the other hand, is used in an engine which has high cylinder temperatures. It has a short heat transfer path, so the nose core insulator will remain cool enough to prevent pre-ignition problems. The shielding used on most aircraft ignition systems is called 5/8-24. This means the threaded portion of the shield is 5/8 of an inch in diameter and has 24 threads per inch. This type of shielding provides adequate protection for most flying. In the rarefied air of high altitudes, however, or while flying through heavy rain, there is the probability that the electrical energy will leak from the lead terminal to the shield. So a special type of shielding called all-weather or high-altitude shielding is available. Here, the insulator is recessed inside the shielding enough for the resilient plug on the harness lead to provide a tight seal. This keeps out moisture that could cause the energy to leak to ground in the terminal end of the spark plug. The threaded end of an all-weather spark plug is 3/4 inch diameter and has 20 threads per inch. Now, one final question before we conclude part 1.